Okay. Good afternoon, everyone. And in behalf of InLab, I'm very pleased to invite our collaborator, Dr. Anna-Maria Olteteanu, to Goldsmiths to give a talk on her research. And a couple of words of Anna-Maria's background. So currently, Anna-Maria is the head of the Cognitive Systems Group in Freie Universität Berlin, and also the principal investigator of the creative problem solving in cognitive systems, which is funded by German Research Foundation. And Anna-Maria has done many things when reading through her academic CV. So Anna-Maria has a multidisciplinary background, so he's a trained pianist, and she has not just one, but 2 PhDs, so something to aim for. The first one on musicology, and second one in artificial intelligence, which was also nominated and won several prizes for the doctoral dissertations. On top of this, in her academic career, Anna-Maria has authored over 30 papers on creative problem solving in cognitive systems, writing a book on the topic. Also, Anna-Maria has been in several program committees as a chair, reviewer, in 20 different conference or journal venues, in many different topics, from cognitive to computational creativity, problem solving, spatial reasoning, and cognitive systems. Also, Anna-Maria has reviewed over 40 papers, edited over 20, and gave more than 30 talks on these topics. Additionally, Anna-Maria is the topic editor of the Frontiers in Artificial Intelligence, Frontiers in Psychology, and Cognitive Science Journal. She's also an associate editor of the Cognitive System Research Journal. Anna-Maria is also an expert scientific reviewer for the European Commission European Commission for Future and Emerging Technologies. And as a sort of like cherry on the top, Anna-Maria is returning to one of her alma mater, so she did her master's in creative computing in the Goldsmiths in years 2010 and 11. Just sort of mention the funding for this visit. Anna-Maria's visit over here is funded by Goldsmiths Research and Enterprise Committee, who gave funding for our collaboration, which is looking at the role of visual and linguistic stimuli in the remote associates task. So please give it up for Anna-Maria Olteteanu.
Introduction. It is a pleasure and very touching to be back here in Goldsmiths, like 8, maybe 9 years later. So this is a special talk for me. And today I will talk about creative cognitive systems in general and the cognitive framework we built, CreaCogs in particular, about remote associations and creativity as one slice of the factors we're studying, and one of the computational systems we built to try to model this and grasp it better. Then we're going to go from cognitive systems to tools, and I'll wrap it up with the InLab collaboration, which is the reason I'm here, and things that we hope to do in the future. Creativity is a highly multifaceted skill. If you've been to an art museum with a friend, it might have happened to you to be completely amazed at what they could see in a piece of art compared to you. I've heard people see in these musical instruments. I don't know if you guys can see them. My guess is maybe here. Then I've heard people say that they can see the prow of a ship coming towards you. Oh, can you see it? Yes, where? Okay. Yeah, that's my guess too, right there. Or a landscape. And I can see a landscape, or features that could be associated with the landscape. Embodied cognition happening there. What's your guess? Okay, so I think it's here, ingredient to the location. Okay, so, but this ability for multiple interpretation in this case, which is a creative ability, is interesting. Yet, how is it really something that we can apply in practical ways to problem solving? And if you happen to bring kind of the same friend with you when you wanted to move to a new place, and you happen to have been missing these objects, for example, a vase or a hammer or a spool of string, the same friend might happen to be very good at finding quick replacements. So they'll tell you you can use a cup to start with for a vase, or a shoe for a hammer, or just how is this called? Tooth floss? Yes, for the spool of string. So you see how, in this case, the same ability displayed in the art gallery can extend to quite practical applications. The creativity does happen in day-to-day life. And of course, it happens at very high levels of information processing. So we have anecdotal cases about various scientists coming up with an idea and previously having some form of imagery that was conducive to the idea. So for example, Kekule, who was trying to come up with the structure of the benzene molecule, reports having had like imagery of a Tibetan knot or a Ouroboros snake before coming up with structure. And then James Watson recounted dreaming of spiral staircases allegedly before contributing to the solution of the structure of the DNA. And we can see how conveniently in each of these cases it could have been that one of these structures contributed in a visual spatial kind of way to the solution. So creativity exists in the artistic, the mundane, and these legendary anecdotes and the scientific discovery. They're all creativity and creative problem solving are capacities that are all around us, and if you think about everything around you, it's actually quite satisfying to discover that someone has had to think of it first, or has had to imagine it first. The question, though, is how can we study creativity in an empirical manner, given that we cannot touch the anecdotes, unless if you have like really tomes of paper from a particular person, you can study their process. And how can we touch creativity and study it across different types of texts? And for me in particular, because of the kind of flavor of research I like to do, which is thinking of the human mind in terms of information processing terms and of computational systems as if they were a mind, one of the questions that is of lots of interest is how can we bootstrap cognition and computation to come up with cognitive AI systems which help improve both cognition and computation. Now, creativity is studied in a diverse way in various fields, and here I'll try to give a brief landmarks kind of mini state of the art to show what the various fields do well, I guess, and what they do maybe not badly, but rarely. So research in creative cognition, that is to say human creative cognition, asks questions like how does a certain cognitive process function in humans, and how can we model it? And what it does, though kind of rarely, is implementations of such theories. And of course there are exceptions, there are always exceptions, though like it was proposed early on that we should have not only like implementations for cognitive systems, but we should also have unified implementation. So we should have an implementation that can account for a wide variety of processes. Research in AI and problem solving has acknowledged a long time ago the fact that there is a difference between ill-structured and well-structured problem solving, but currently we focus mostly on well-structured problem solving. So we ignore this creativity of the programmer that takes a problem which is ill-structured, makes it well-structured, and then we can apply an algorithm to it because someone else has structured it. And computational creativity, finally, does creative systems in a wide array of fields. So creative systems that can do a bit of mathematics, music, art, poetry, to magic, thinking of one of my former colleagues here at Goldsmiths. But it very focuses on cognitive mechanisms, the exception that I know of being focusing on concept blending. And the evaluation theories that come up in computational theory, in computational creativity, are generally very different from the evaluation theories that appear in creative cognition. So the approach I'm going to talk about today proposes a mix of methods between these three levels. The first level is that of human cognition, with the tools given by cognitive science. The second is the computational level, implementing systems capable of similar reasoning and creativity tasks as humans. And the third level is this coupling between the two, because I do believe that if we manage to do a form of coupling, we can boost the results of each of the fields. Okay, and before we go on, I inserted a brief note on computational cognitive systems, which are defined as systems that take inspiration, simulate, or aim to replicate cognitive process, type of knowledge and performance. And of course, there is a huge continuum of cognitive systems, from the shallow to the deep end, or at least that's how I imagine it. Some systems only aim to take inspiration from the human domain and like build AI systems that can do these kind of skills and they do them better than humans. And other systems really try to model human results, the errors and all, trying to understand how the human cognition works. And because there are very many types of creative capacities, in our previous work, there is a cognitive framework. It's the Cracov's framework, and it's anchored in cognitive theory. So we're trying to find a unified way to tackle these very diverse creative cognitive skills. And we try to tackle a wide diversity of them with a small set of processes. And probably the main thing you need to know about is that our hypothesis was that the knowledge organization in a system, in a cognitive systems, be it natural or artificial, supports the creative process. And this is the type of knowledge organization which we came up with. I'm not going to enter in much detail about it. I'm happy to give more details after the talk. But it has three levels. So it has a feature space level where you can do machine learning if you want to, which acts as concept anchoring. It has a conceptual, symbolic level, and it has like a structural level where you can do problem templates and knowledge fragments and scripts, if you know those various theories. And the reason we propose this is because it could support a variety of search processes, of association and creative inference and insight at all of these levels, navigating the various levels and replacing various pieces of knowledge with other pieces of knowledge within the framework. And we believe these processes can help us computationally simulate a variety of cognitive skills. And what we focused on so far, and for example, in order to grasp a cognitive skill, like for example, creative associations, we try to have some form of an evaluation. And if we can find a form of evaluation that is within the human realm, that's even better. So for example, creative associations, we evaluate currently with the remote associates test, and we would like to evaluate with other tests too. Creative object replacement, which we have another system for, we evaluate with the alternative uses test, and we have creativity in practical daily tasks. I know that sounds broad, but we have a specific set of processes for that. We evaluate with insights test. And this to have been done, this is in work, we already have results, and we think that in the future, probably we're going to be able to do re-representation. So tasks like ambiguous figures and pattern making tests. But today, I'm going to focus on this line, so on creative association. In creative association, it's generally evaluated with the remote associates test, which is a test Mednick came up with in 1962, and has a base in his theory of associative creativity. So the way it's deployed is as follows. Participants are given these three words, like cottage, Swiss, and cake, and they're supposed to come up with the fourth word that will relate to each of them. And if you're a native speaker, you have an advantage here, of course. Anyone try to solve it? Okay. Now, Mednick's theory is that the better you are at this, the better you are at the associative factor in creativity. So if you were to formalize this in a very simple way, a computational system solving the remote associates test, you take three-word queries, and we'll come up with a word that is related to all three of them. crackles. This works by having things at the concept level, activate the knowledge fragments at the problem template level, and hopefully coming up with a convergence. That is this pop-up moment for when people report insight, they report having a word pop in their mind, not necessarily a search. So, in the context of this query, you'll have falling actor and dust, triggering all sorts of expressions in the mind of the solver, and hopefully there will be a convergence upon a word, which in this case would be. Okay. So we implemented this as a system using this process in Computationally, and here's a visual depiction of the computational process at the concept level only. So you have cottage, Swiss, and cake. Each of them activates a variety of associates. For example, Swiss activates ball, Alps, army, chocolate, cheese. And each of them does the same. And it might be, obviously these are just a few of the things they activate because I can't show absolutely everything. And it might be that you find a 2-item convergence. For example, chocolate is activated by both Swiss and cake, or a 3-item convergence, for example, cheese, which makes for a good answer because it's activated by all 3. And it might be that you have multiple convergences here too. So it's a matter of which convergence the system will come up with first. And Computationally uses, of course, knowledge. It uses 2 grams, that is 2-word expressions, for American English to populate its knowledge base. Now, to evaluate its performance, we wanted to test the system to queries that are normally given to humans. So we tested against this 144 set of normative data queries by Bolton and Young-Beaver. So these are queries for humans that give like reaction times and accuracy that people would generally have as a mean. And you can see that the system answers 64 of the 144 queries correctly, when in 47 of the cases 3 items are present, and in 17 of the cases only 2 items are present, and this is when there is not enough answer knowledge. So, for example, the system only knows Swiss and cheese as an expression, it knows cheesecake, but it doesn't know cottage cheese, and it can still come up with cheese as an answer. So, of course, starting from no items known to all 3 items known, the more knowledge you have in the system, the better the solving. But also, there is this interesting capacity for plausible new answers. And before I get to that, we are also interested in this part where the system comes up with answers despite only having 2 of the knowledge fragments, because it has implications about robustness of processing in AI when you're missing parts of information. What are plausible answers? Well, when Bodden and Young-Beaver were coming up with their queries, they provided 1 correct answer to each of them. So these are the rat queries. These were the correct answers. So if, as a human, you were answering exactly this answer, your answer counted as correct and the response time was measured. However, they didn't account for the fact that sometimes different answers might be the case. And we had the pleasure to find that Computationally was indeed coming up with new plausible answers. Plausible answers being answers that, evaluated by a human that doesn't just think of this correct answer, will be considered potentially correct. For example, if you take home, see, and bed, would the correct answer sick, because homesick, seasick, and bedsick? The new plausible correct answer is water, because water homes, sea water, and water bed. And though these answers, the plausible and the correct answer, are here in different semantic domains, it also can happen that they are within the same semantic domain. Like here, brain and body are within the same semantic domain. I guess battle here and war too. Now we wanted to check whether the difficulty of solving queries by humans was similar in any way with the difficulty of this convergence process we were doing with Computationally. So it's probably useful to tell you here that we were using the frequency of the 2 grams to generate an activation value. So for example, if you gave the query word A, and you're expecting the answer word WX, the probability that you'll get WX given WA, dependent upon the frequency that WA, let's say cottage, appear together with the answer cheese over all the cases where WA appeared within our corpus. And then we weighed each of these probabilities for each of the 3 query words equally. Though of course one can model this as they like. One can probably assume that the first one has a stronger weighting because we read from left to right. So we compared probability based on frequency to human difficulty, response times, and percentage of queries answered. And we compared directly to the probability coming from, so the probability coming from our system with the Bowden and Young-Beeman data. And Bowden and Young-Beeman gave all his queries at different time intervals. So he gave them at 7 seconds, 15 seconds, and 30 seconds. And we see that there is a correlation that is significant at all 3 time intervals. So this is correlation on accuracy at all 3 time intervals. And then correlation on response times is also significant, but it's inverse. What does this mean? Like the faster people are, then the higher the probability. Is that correct? Yes. So the knowledge we used was we started with 1 million most frequent n-grams from the COCA corpus. Then we only selected 200,000, which were relevant for our task. That means things that were nouns and verbs. So we selected on part of speech, basically. We didn't select on whether we will have enough knowledge to solve the queries. And the system came up with correct and plausible answers, and it correlated with human performance, which was pretty satisfying. So then as a next step, we were thinking about taking the system to a tool level. Because now that we established a computational point, we wanted to use this cognition computation bootstrap. So we also wanted what it would mean to generate computationally tools for cognitive science, where humans would help evaluate the quality of the computationally created items, and then these items can also be used deeper to explore the human creative process. And the reason we did this, we've done it with some of the others too, but the reason we did this with the remote associates test was that cognitive psychologists administering this test don't have enough control over variables, and there is only a small normative data set, so only these 144 items. While they have in control of the variables, I mean, they don't know frequency of words. They don't know, let's say you would want to give a specific set of queries that were using only a specific set of words. You couldn't do that. So we're wondering how we can enable this. And if you remember the visual depiction of solving the rat, if you stare at it for long enough, you will realize that the same knowledge organization process can be also used to generate queries. Because each node in the network, like for example Swiss, which was a query word before, can also be seen as an answer word, as long as it's connected to more than 3 items. You see it? So we took an answered center approach. We took all the words in our knowledge base, we looked at all the things that were associated with each, and we considered them as potential answers if they were associated with more than 3 words. Then we calculated a probability for each of these, and then combinatorically we constructed a set of queries. So, whereas we started with a not enough control over variable situation, now we had, with Comrade G, we had generated a span of 17 million queries in American English. And of course we need to evaluate these queries because we don't know how they look like until we have them. And we want to do this evaluation with human participants. So what we did is we took human participants that solved Comrade G 50 queries randomly chosen, with Bode and Young-Beeman 50 queries randomly chosen. And we see an accuracy within their solution. In both, we see a correlation in their solution, both in accuracy as percentage of queries solved and in response times. And this is done with 113 people, with 112 here, because I think someone fell asleep because he had like more than 5 hours of answer time. I can. And then we've done Cronbach Alpha. This is to see whether we could validate our new tool, and we've seen that Comrade G had a high score over 0.7. It's acceptable, and 0.85 was good on accuracy, and 0.99 on response times was great. And they also deployed an interface for this so that cognitive psychologists can select a number of queries and then use a variety of factors to choose whatever they want out of them. It's still limited to a certain extent, but this gives them queries. And as you can see, the query is kind of good. So investor offering portfolios with answer stock looks like a perfectly fine query. Then, I don't know, changes, cliffs, urchin, C, looks like a good query. And we also offer all these factors for each of them because we wanted to give control over frequency of query words, of answer words, probability of each, and then control over what words are in the query or what answer there is. And we can, with a bit more digging, we can also give data sets relating to number of potential answers and combinations of all the factors above. And because we had the data set, we wanted to see whether it's really useful. So we thought, okay, let's try it with probability and frequency. So what we wanted to do is we wanted to basically have two knobs modifying frequency and probability while controlling for every other factor. So we turned our data set into bands. We wanted to do like a 2x2 design and ANOVA with probability on low and high and frequency on low and high. And we found bands, for example, low probability for us meant lower than 0.2, high probability between 0.4 and 1, and then frequency between 20 and 75 encounters of the query word and the answer word, and high frequency over 250. And we did, lo and behold, find enough queries to run a 2x2. Very little queries here still, but we could select randomly 20 queries from each of these and do the ANOVA. And this is what we've got. So we've got the following main effects. So we've seen that frequency affects accuracy and probability affects accuracy. Frequency affects response times, probability affects response times, and very interestingly, there are no significant interactions because we're expecting like frequency modulates our probability calculation, obviously, but apparently there are no significant interactions. So whoever wants to model this further will need to like kind of separate the strength of the associate versus spread and convergence. And we're quite happy and ready to start now thinking about what makes a good human associates test query, right? Not just computationally generating it, but what does it make it to have a very interesting creative query. When we came across a further complication, which is the functional rat complication, because it turned out that two researchers in about 1971 argued that Medlink's original queries were not uniform. So what did they argue about? They actually did like query's idea of the remote associates factor, but they argued that his data set of queries that he composed was not even because it contained at least two types of queries. So it contained structural association-based queries, which are queries where the association between the query words and answer would be like the association between sweet and potato. So sweet potato is something that appears in language. We call it a compound. He called it structural, and so is black magic. And he differentiated functional association, like the association between flower and daisy, that don't appear in language one after the other. Maybe they appear in neighborhood, but still. Or bird and feather. So associations that go beyond language. So we wanted quite happy to experiment with the data set, but the queries were supposed to be in some appendix to the paper. You're not together with the paper, in some library, and the library moved all their material. You're supposed to send it to the Library of Congress. The Library of Congress didn't have them, so somewhere they got lost in transport. No queries existed whatsoever. So we decided to turn this problem into a research problem, rather than let it stop us, and use Comrade G to try to generate functional queries instead. And because one of the arguments Gordon and Clark was that medmix queries are not so good because some of the associates don't appear in the Polar-Jenkins association, we decided to use, albeit a more modern free association data set from the University of South Florida as a knowledge source for our generation. And basically this data set gave a lot of people keywords like abundance and asked them to come up to freely associate things. For example, people came up with famine, food, full, and this was keyword and the target word. So knowledge base was similarly organized to our compound generator, and then we found like a standard for the frequency and the probability metrics, specifically the target word and the target word when given a specific cue, so that we have the metrics too. And we obtained 30 million functional rat queries, which look like this. So, clockwise, left, and wrong. Answer, right. If you notice the relationship, so clockwise can mean right, left and right are in antonymy, I guess, and so are wrong and right. So the relationships are not linguistic. Then astronomy, moon, twinkle, with answer star. Again, functional relationships between star and astronomy, star and moon, twinkle, star. I guess that could be compound too, but we couldn't avoid them to start with. So we could see that they were different from compound ones because they contained antonyms, synonyms, then parts of, like for example, finger, hand. It's a functional relationship where one is part of the other. And we are ready for validation. So our first validation study was with 26 people of the previous Comrade G testing lot. So we called people that have solved compound queries, and we gave them 75 functional rat queries, and we saw that there was already a correlation between accuracy between the two and correlation in response times. But this was only broad significance, and it was because probably online we only got 26 people to come back from the Comrade G queries. So then we run it with more people, and we run it by giving side by side the functional rat and the compound rat in both forms, from both Young Beeman and from Comrade G queries, and we can see the same correlation pattern. In fact, this is very high correlation, probably because we gave, I mean, there are other factors at play, like personality and speed of solving in general. So we see that accuracy has a high Cronbach alpha again, and response times too. So the functional rat turned reasonably well, and now we can give that to as a tool for creative science. And now that we're kind of satisfied that the process of generation works all right, we started asking questions about modality in general. If the Comrade G process could be applied to create queries in a different modality. Because there exist creativity queries for both language, not just the remote associates test, and for visual creativity, I guess, this is an insight test, but there are many others, but there are no tests in both modalities. So the idea was if we could maintain processes, so have something that can be solved both visually and linguistically, but transfer modality. So something like modality translation. We tried by starting from our initial formalization of the remote associates test. So to recap, 3 query words are given here, and the answer is Yes. Okay, so if each of these is a word A, word B, word C, there is an answer word. We looked at this and we thought, okay, if we don't think of this at all as if they were words, well, we know if they're words that word A and the answer word have to co-occur or have some form of a relationship. And the same from word B and answer word. But let's say that they're not words, but elements of perception, things that you can see or hear, or something like that. So if this was a visual element, B was a visual element, C was a visual element, then the answer has to be a visual element that co-occurred with either of them or appeared within their neighborhood proximity of experience. And it was encoded like that by the solver. And this kind of thinking made us come up with this kind of query. Let's see at the visual one. The answer is, this is not fair because I haven't shown anyone yet. I'm giving you the answer, but let's see. Yes, that works. And here. Table, yes. The table is the more narrow one. We kind of like the more narrow one, right? And so you can see how that would have co-occurred with either of them, and we removed it from there. How about this one? Let's do a bit harder. But I should have 5. Harder indeed. Remember what the norms are. So the answer is fork, which is not fork as a linguistic term, but fork as a visual answer. Because it's a trident in the case of Poseidon, and it's a fork in terms of the knife, and it looks kind of like a fork for moving hay here. Right? So it's a purely visual answer that wouldn't work for language. Okay. And our preliminary test, 56% of participants claim to come to the solution visually, which is great, but it's self-report, so we can't really trust it. So they did come up with very interesting other self-reports, like one of our answers was supposed to be fire, and some people reported feeling like warmth before coming out with this answer. We have no idea if that's true anyway. But then we evaluated the visual rat, again, by comparing it first with Comrade G-score, people that have done compound queries, and then in a second study with really a lot of people giving it side by side. So we gave side by side visual queries, compound queries in both forms, and we see the correlation is still there. And this is where our in-lab collaboration also comes into place, because one of the advantages of the visual graph is that given that it is a valid measure, and we're refining it to be a valid measure, and a very precise measure, it can be used cross-linguistically. So together with our partners, Temu and with Vlada, we have investigated whether the visual graph showed reliability across different languages. I mean, we investigated the cross-cultural differences too, but from our Krakov's perspective, it's interesting whether the visual graph can hold over various languages. And to give a very brief summary of very interesting results, we have explored it over Russian and Finnish samples, and we see the correlation is between visual rat and linguistic rat is there across languages, both Russian and in Finnish, both in accuracy and response times. Now, we very much believe this is just the beginning. And then direct follow-ups from the work within lab are, could these factors, the difference between languages, be really mapped out in terms of information processing, structure? For example, different languages might have more frequent compound words versus others. We're interested in the cognitive factors there. And we haven't really done a split between the Finnish and the Russian compound versus functional items. We would like to computationally develop Finnish and maybe Russian remote associates test, but we think this is a challenge because, well, I don't understand any of them, so our partners will have to really cook with whatever comes out of the machine there and evaluate them. And then a broader way in terms of creativity and associations, we're currently building a computational solver for the visual RAD, and we would like to explore multiple answer queries. So multiple answer queries were suspected to exist, but they were first only showed computationally using ComRAD-G, and we can really systematically check them out with ComRAD-G. We would like to take the remote associates test to other sensory domains, like I would really like to take it to auditory and smell. I've been trying to discuss with perfumers what is their idea about the smell association, but it's really hard to pin down. I don't know if this is hard to pin down because they are perfumers, so therefore they'll think about it in much more complex terms than what we need for the test. But anyway, and we would like to come up with a new case study for creative association, so different way of evaluating. And one of the things we thought about is a code names application. So in short, I hope to have showed you that formalization and implementation of cognitive AI systems can have fruitful impact on cognitive science, on tools and models, and in particular in creativity science. Thank you. And now I'm ready for questions.
Thank you, Anna Maria, for the fantastic talk. Do we have questions in the audience?
I'm actually quite interested in the bit that you didn't talk about in following up. So obviously you're focusing on divergent thinking tasks in the rats. Do you think, was it more challenging to create a cognitive system that came up with convergent solutions? To me, it seems like a very differently structured problem, even if you're working with kind of associations and concepts.
Yes. So I guess the bigger difficulty, it's a very good question of whether difficulty transfers across tasks, I guess. We consider the association to be like divergence and then convergence.
Yeah.
And the difficulty generally consists for us when modeling and trying to implement a system in is there data, is there knowledge? Because we like to have cognitive knowledge, like with the alternative uses task, which is, it's a creative task about giving an object to people and they tell you what you can do with it creatively. Which we have modeled, but our main problem was, okay, where do we get knowledge about objects and their uses in general? And then we got knowledge about, so our theory with that was that property of objects, when it comes to physical objects, will play a role. So we kind of think that, for example, physical properties, people, what they'll do is like they kind of implicitly think that if two objects have similar properties, maybe they can transfer affordance without overtly showing you this. So we had to encode properties of objects too, to then show that it can be solved and our systems come up with creative things. And like when it comes to insight tasks, for example, it's like insight tasks with practical objects, lots of objects that are very knowledge heavy. I think that's the main hardship. Yes.
So when you did the ANOVA for the conditional probability and the frequency, was that, so that's the frequency of the query words or the frequency of the keywords?
So the frequency of the query words will co-occurring with the answer word, if they co-occur.
Yeah, yeah.
So or with all the other words.
Yeah, so I'm just wondering, so the frequency has so the frequency is the main effect, and there is no interaction. So does that kind of mean that, so even when the conditional probability is low, as long as the words is very frequent, then you still get the correct answer? Then that sounds a bit counterintuitive.
Right. So it means that somehow we have to differentiate between two concepts that are very close to me and probably to you too.
Yeah.
This concept of one word being strong association or something, right?
Yeah.
And
Should being frequent wouldn't be enough, right? It doesn't
right.
co-occur with the other.
But it also depends on how many other attachments each of the words has, right? So that's the probability part.
Yeah. Yeah. But the frequency alone would have a main effect.
Yes.
So that really means that the attachment part doesn't really matter.
Well, the attachment part matters in its own. Yes.
Yeah, in
So we should model them separately. We
Okay,
have
yeah.
that, yeah.
Yeah, do you have an explanation for that finding?
No, I think it was quite non-intuitive and interesting. This is part of why we should, I guess, scientific experiment, because like, in our intuition sometimes not whole.
Yeah.
Yes.
Can I just maybe quite broad and sort of like your opinion, like what is your take on the sort of like the matrix theory of the associated creativity, sort of as a measure of individual differences, for example? That, do you think that people who are better solving this kind of thing are more creative?
Okay, so let me answer that. Like, I think what I like about creativity measures is that people can be very good at one and very bad at another, because this means that there is no like one measure of creativity. And this means that there is hope that if you score very low on one, you might get you're very creative in a different way, or that you can fail. So yeah, when it comes to individual differences, I like to think of it more like that, and I don't think one of the factors capturing individual differences is the enough anyway.
Do you have any further questions? Excellent. Anyway, Anna-Maria is going to be here for a couple of more days, so if anybody has some queries on mind, just contact me in the email, I can pass it on to her.
Or some creativity task.
Okay, so maybe round of applause one more time.